Hello dear students, welcome to ArcNX. In this series, we are looking at different shortcut methods to solve complicated questions asked in NEET and JEE examinations. Okay, and today we are going to start off with a method called nodal analysis method or zero potential method. And this method helps you to solve very complicated circuit questions very easily. Let's go straight away to the topic. I have a sample circuit given here, and the circuit has few resistors and cells connected. Okay, now if you use this method, you will assign zero potential to a common point. As you can see, this point, and this point are connected together, and there are no components, cells or resistors connected between these points. So if I assign zero potential to this point, same potential comes right here, and this point is also at same potential. If you walk along this line, as you walk, you don't find any resistors or cells along the path. So same potential stays at all these points. Okay. Now for other points, try walking along the path, and as you walk, if you meet a cell, see whether you meet negative or positive of the cell. If you meet the negative, you should raise the potential by that number, and if you meet the positive of the cell, you have to reduce the potential by the same number. Okay, so let us look at this now. I'm walking along this path and I see the negative of the cell here, which means I should raise the potential by 2. So when I come here, this point will be at a potential 2 volts. Okay, and I walk along this, I see the negative of the cell. So this point has to be at 3 because I'm raising the potential by 3 here. So this point has to be at potential 3 volts. Same way, if I walk along this, I meet the negative of the cell again, and as I walk up, this potential has to be raised by 5, and this point comes to be at potential of 5 volts. And for the common point here, I can take the potential as x volts because it is an unknown quantity. Now I can find the current through this branch by taking potential difference across this divided by resistance of that component. Okay, same way I can find the current here, or if I have another resistance here, I can find the current there. Now this is how you use zero potential method to solve questions in circuit analysis. Okay, so let's go to previous questions now. Question number 1. This is a previous NEET examination question. If the galvanometer G does not show any deflection in the circuit shown, the value of R is given by. So galvanometer does not show any deflection. Galvanometer does not show any deflection means the current through the galvanometer has to be 0. Okay. Now let us assign a potential 0 volt to this point. So this point also has to be at 0. This is also at 0. Because if you consider this path, there is no resistor along the path, no cell either. Right. And if you walk up along this path, you cover a 2 volt cell, which means the potential has to be raised by 2, and this potential comes to 2 volts. And if you walk along this path, you have to raise the potential by 10 volts because you are meeting the negative of the cell. So this point is at plus 10 volts. Okay. And along this, this galvanometer is ideal, which means it does not have any resistance. So this point's potential has to come as such at this point. So this is also at 2 volts now. Now, how do you find the current through this 400 ohm? I can find the current through 400 ohms. Look at that. See the direction of current there? Because this is 10, which is higher potential in comparison with 2 volts. So for finding current through 400 ohm, I have to apply Ohm's law. Ohm's law is what? Current is given by potential difference divided by resistance. Potential on the left side is 10 and on the right side it is 2. So for this resistor, potential difference between left hand and right hand is what? This is 10, this is 2. So that has to be 10 minus 2 divided by the resistance there is 400. I'm applying simple Ohm's law, 400, and that makes it 8 by 400, or it is 1 by 50 amps. Okay, so the current through this branch is 1 by 50 amps. And when the current reaches this junction, zero current flows through this, which means the entire current begins to flow along this path. Okay, so I can write the current through this branch as 1 by 50. Okay, because the current that flows through 400 will be flowing through this resistance as well. Now across this resistance, I can apply Ohm's law for one more time. For this resistance, how do you apply Ohm's law? I'm writing Ohm's law here. I is equal to V by R again. Look at that. I there is, for this path, I is 1 by 50. So 1 by 50 is equal to, for this resistor, potential differences, this end is at 2, this end is at 0. So the potential difference across this resistor is 2 minus 0. 2 minus 0 divided by the resistance is to be calculated here, right? So I'm putting it as capital letter R. Now cross multiplying, R is equal to 50 into 2 minus 0 is 2, 50 into 2 is 100 ohms. So here the answer is option 2. Okay, right. Let's move to the next one now. Find currents through all the branches. See, again, we have a circuit which has few cells and few resistors. And as per the method, I need to assign a potential of 0 volts to a common point. Now look at the common point. I'm going to take this point as my common point. I'm assigning 0 potential to it. And if I walk to the right, I see cells positive, which means I have to lower the potential by 12 volts. So 0, this is lowered by 12, which means here it is minus 12, minus 12, minus 12. This point is at minus 12. Okay, this point is at minus 12 volts. Now, if I walk along this, I see the negative of the cell. When you meet the negative, you have to raise the potential by that number. So this point, after this point has to be at 6 volts. You are raising it by 6 volts. Okay, I have a third branch now. I walk along this, I see the positive. When you see the positive, you have to lower the potential, right? So 0, minus 8. You have to reduce it, minus 8. So this has to be minus 8, minus 8, minus 8, minus 8. This point is at minus 8. Now I can easily find the currents. Tell me, look at this. I'm going to mark the current this way. I'm going to call it I1. Now they have given the current direction to the right, but I have taken it to the left. Why have I taken it that way? Because as you can see, this end is at 6 volts. This end is at minus 8 volts. So 6 volt is higher potential in comparison with minus 8. So current has to flow this way, right? Current flows from higher potential to lower potential, isn't it? So I'm going to find I1 now. What is I1? I1 is equal to potential difference. For this resistor, potential at the right end is 6. Potential at the left end is minus 8. So potential difference is 6 minus minus 8 divided by the resistance on that branch is 28. So 28. 6 minus 8 is 6 plus 8, which is 14 by 28, which is equal to 1 by 2 amps. Now let us look at the second current, the current to the right. Again, as you can see, I have reversed the direction of current. They have given the current to the left, but I have taken it to the right. You know why? Because this point is at 6 volts, which is obviously greater than minus 2 on the other side. If you compare 6 and minus 12, 6 is greater potential, so current has to flow to the right because current flows from higher potential to lower potential, right? So I'm going to find the current through this branch now. Tell me how I'm going to do it. I2 is equal to, I'm going to call it I2. This is I2. I2 is equal to potential difference. Higher potential is 6, lower potential is minus 12. Across this I have to find the current. So 6 minus minus 12 divided by the resistance there is 54. So that will make it by 54. 6 minus minus 12 is 6 plus 12, which is 18 by 54, which is equal to 1 by 3 amps. Now see how the currents are flowing. Look at this. I1 flows this way. Okay. I2 flows this way. They come together at the junction and they flow together as a single current I3. And look at the figure. They have given I3 in the downward direction. But I know that the current is going this way up. This current is also going this way. So they have to add and go up like this. So how do I find my current? I3. This is I3. I3 is in fact going up. I3 is going up. So I3 is nothing but I1 and I2 combined together, right? So that is how I'm going to find I3 now. I3 is equal to I1 plus I2. I1 is 1 by 2. I3 is 1 by 3. So if I take LCM, it is 6. And on numerator, I have 3 plus 2, which is 5. 5 by 6 amps. See how simple the solution is. Okay, right. Let's move to the next one now. Again, it's a previous JEE examination question. In the following circuit, C1 is 12, C2, C3 are 4, C4, C5 are 2. Charge stored in C3 is. Again, I have a common point here. Look at that. These are all connected together, right? So I'm assigning 0 potential to this point. So this point is also at 0. This point is at 0. This point is at 0. Look at that. This is 0, this is 0, this is 0, this is 0. Because all are connected together. There is no component along the path. Resistor, cell, nothing. Capacitor, nothing. Right. Now, if you walk along this, you see the negative. So raise the potential by 2. Increase the potential by 2. So this point comes to be at 2 volts now. And if you walk along this point is at 2, isn't it? You continue walking. This point is also at 2. So I'm writing them. This is at 2. This is at 2. So all these points are at 2. Okay. Now the question is, the charge is stored in C3. So I'm concerned about C3 alone. Look at C3. This is C3. Okay. I need to find charge through this. How to find the charge? Q3 is equal to C3 into V3. Right? You learned the equation for charge as product of capacitance and potential difference. Right? So what is C3 here? C3 is given in the question as 4 mu f. So 4 into 10 power minus 6. Micro means 10 raised to minus 6, right? Into V3. What is the potential difference across C3? This end is connected at 2 volts and the bottom plate is connected at 0 volts. Look at that. For this capacitor, one end is connected at 2 volts, the other end is connected at 0 volts. So the potential difference is 2 minus 0. Right. Potential at the top is 2, potential at the bottom is 0, potential difference is 2 minus 0. Very simple now. 4 into 2. 2 minus 0 is 2. 4 into 2 is 8. 8 into 10 raised to minus 6 coulombs or 8 microcoulomb is the final answer. Okay, again a very simple question. If you do it this way, right. So let's move to the next one now. This one is a little complicated. Find the current through 5 ohm resistance. Look at this. I need to find the current through this 5 ohm. For that, what I'm going to do is I'll assign a potential of X volts to this location. Okay, X volts to this location. All right, or let's take it as 0. Let's make it simple. It is 0. Okay, and let's take X for this location. All right. Now my job is to find the current through this branch. How to find the current now? I can use Ohm's law. Current is given by V by R. What is V across this potential difference? The right end is connected at X, left end is connected at 0. So the potential difference between them is X minus 0. Look at that. Potential at the right end is X, potential at the left end is 0. So potential difference is X minus 0 divided by the resistance is 5. Resistance is 5. That is X by 5. Now the question is very simple. Now my only challenge is to find the value of X and put it over here. That's it. Okay, so I'm going to find X by some methods now. For that, I'm using Kirchhoff's current law. I'll tell you about it later in another session. According to Kirchhoff's current law, the algebraic sum of currents reaching any junction is equal to 0. All right, so at this junction, I'm going to apply KCL. KCL says what? the algebraic sum of currents reaching any junction is equal to 0. So I'm going to mark the potentials at all other points now. Look at that. This point is at x. So if you walk down along this path, you meet the positive, which means you have to lower the potential by 40. So this point is at x minus 40. So if you come along this point is also at the same potential. This one is also at same potential. This one is also at same potential. Okay. I'm going to mark them all. X minus 40 here. X minus 40 here. X minus 40. Right. Everywhere I got x minus 40. Right. Okay. Now if you walk up along this. Okay. Let's keep it there. If I walk up along this is negative, which means I have to increase the potential by 20. Okay. So x minus 40, right here I have x minus 40. I'm increasing it by 20. So this point is at what? X minus 40 plus 20. That is minus 40 and 20 together, minus 20. So this point is at x minus 20. Similar way, this is at 0. When you come over here, you see the negative. So raise the potential by 10 here. Because when you meet the negative, you should increase the potential by 10. So this point comes to be at 10 volts now. Okay, so I marked all the potentials now. I can apply Kirchhoff's junction law. So how to apply Kirchhoff's junction law or current law? The algebraic sum of currents reaching any junction is equal to 0. So I'm going to apply that to this particular location. How many currents are there? Current number 1 along this path. Current number 2 along this path. Current number 3 along this path, current number 4 along this path. Right. I'm going to write all the currents and then sum them up and equate that to 0. So let us do that now. First current, this is what? Potential difference is x minus 0, resistance is 5. So that is my first term, x minus 0 divided by 5 plus. Now for this part, okay? For this part, it is x minus 40 is the potential of this point. 0 is the potential of this point. So potential difference is x minus 40 minus 0. That is x minus 40 itself divided by the resistance here is 10. Divided by 10 plus. Now as for the third part, look at that. This is the third part. Tell me, this point is at x minus 20. This point is at 10. So the potential difference between them, it is, I'm writing here x minus 20 minus 10. Look at that. This is x minus 20. This is at 10. So x minus 20 minus 10. So that makes it x minus 30. Keep that in mind. It is x minus 30 divided by the resistance on that branch is 10. So I'm going to put it here 10 plus for the last part. Look at that. The last part, this one. All right. The potential at this location is x minus 40. So this is also x minus 40. This is 10. So the difference is x minus 40 minus 10. That is x minus 50. See it again. For this resistor, the left side is at x minus 40. Right side is at 10. So the potential difference is x minus 40 minus 10. That is x minus 50. X minus 50 divided by the resistance for that branch is 10 should be equal to 0. Algebraic sum of all these currents should be equated to 0. Now I can simplify this. The LCM here is 10. I'm going to write it on the next page. LCM is 10. Okay. 10 on the denominator. For this, I have to multiply this with the 2. This also has to be multiplied with the 2. So that makes it 2x, right? On the numerator, I have 2 times x plus. All of the terms have like 10 on the denominator. All right. So I can write the numerators as such. X minus 40, x minus 30, x minus 50. X minus 40 here, x minus 30, x minus 50. X minus 40 plus x minus 30 plus x minus 50 should be equal to 0. Now let us cross multiply. 10 times 0 will be 0. What's on the left side? I have like a 2x plus x3x plus x4x plus x5x. So I have 5x on the left side. Then minus 40 and minus 30, minus 70, minus 50, minus 120. That will go to the right side to become plus 120. So if I take x, that's going to be 120 by 5 or 24 volts. See how simple it is? So I can find the current now. I just have to substitute for x here. The current is given by x divided by 5. X value is found to be 24. I'm going to substitute it here. It is 24 divided by 5, which is equal to 4.8 amps. We can easily solve this question using KVL also, but this one is much easier and better. Okay, right. It's actually a complicated question. See how simple the question is. So let's see the last question now. I'm going to leave it as a homework for you, but I'll give you the hint for this. Right. So as you can see, this is a Wheatstone's bridge, but it is an unbalanced one. How do we know that it is an unbalanced one? Let us check the condition. Now this is called left top, this is right top, this is left bottom, this is right bottom, and this one is central arm. Okay, and the condition is left top by right top. That means 5 by 10 is equal to 1 by 2 has to be equal to left bottom by right bottom. Left bottom is 10, right bottom is 5. 10 by 5, which is 2. Are they equal? No. This is 1 by 2, this is 2. They are not equal, which means the bridge is an unbalanced one. For unbalanced bridges, you have to use either this method or you can use delta star conversion method. Okay, anyway, I'll tell you about this method now. What you can do is, you'll connect any random cell across this. Some random cell across this. Okay, I'm going to put 100 volts here. Okay, this is 100 volts. Now, if that is 100 volts, the left end of this, look at that. This is 100. So, the left end has to be at 100 volts. The left end of this is at 100 volts. The right end, the negative terminal is at 0 volts. That is the meaning of potential difference being 100. Okay. Look at that again. I am connecting some random cell to the circuit. This is 100. So, the left end is at 100 volts, right end is at 0. Okay. And by symmetry, the current through this branch, if I take it as A, the current through this branch also has to be A. Why? Because this is 5 ohm, this is also 5 ohm, right? Same way current through this has to be this, same as this. Okay, so if I call the current through this as B, this is also going to be B. Look at that. This total current is A plus B. Here the total current is A plus B. So the current flows in as A plus B. Right here, A goes here, B goes here, and it flows out as A plus B. B from here, A from here. Right. By symmetry, you can say that the current here and current here are equal. The current here and current here are equal because the resistors are equal there. Right. Now, I assign a potential equal to X volts to this location, or rather this location. Okay. Now, that would definitely make this location's potential 100 minus X. I'll tell you why. Because look at this part. What is the current through this branch? Voltage by resistance, right? Potential difference by resistance. Potential here is X. Potential here is 0. So, X minus 0, that is X by resistance is 5. So, I know that this current is X by 5. So, this current also has to be X by 5, right? That is also A. How do I get X by 5? Let's check it out. This is 100, no. This is 100 minus X, no. So, when you take the difference, hundreds are gone, right? So, minus or minus X plus X. I'll do it here. 100 minus 100 minus X. Left end is at 100. Right end is at 100 minus X. So, the potential difference is 100 minus 100 minus X. By the resistance there is 5. Alright. 100 minus 100 is 0. Minus or minus is X. So, I get X by 5. Exactly what I got here, no? So, if the current here and current here are to be the same, I need to take this potential as 100 minus x. Or you can try doing the same thing to this and this as well. All right. Now that I got a location with a potential x, I can finally apply Kirchhoff's junction rule to this location. Okay. So I'm going to write it here so that you can take it as an assignment. Apply KCL here. Okay. And you'll get an equation in x and solve it for x, and then find the resistance by taking total voltage by total current. Total voltage, you know, it is 100 given here. Okay. 100 given here by total current. What is the total current? Look at that. Current here is A, current here is B. So the total current is A plus B. So once you have found the values of A and B, you can put them over to this equation and then solve it for finding effective resistance of the circuit. Okay, there are much better and easier methods, but I thought of doing this question using nodal analysis method as well. Okay, so that's all about this episode. We'll come back with another session on another topic later on. So till then, bye.